you're on task, you should have been good. If you have a function within a function like you do here, then you need to, first of all, remember use the chain rule. Second of all, identify what's inside, what's outside. In that case, what's inside? Sine, and outside is 1/2. How do you take the derivative of blah to the 1/2? Derivative is on a power rule is 1/2 comes down, drop it to the negative 1/2, and what's inside stays inside. Right? So the derivative on the outside, but then times the derivative of the inside. What's the derivative of sine? Cosine. That's your result. How'd you do? Okay. This guy, is that sine times square root of x and therefore product rule, or sine of square root of x and therefore chain rule? Oh, okay, so this is more like, it is a chain rule, but as far as what's inside, what's outside, now the outside is sine and the inside is the 1/2 power. So take the derivative of the outside. What is the derivative? That's y. Oops, this is terrible notation what I did here. This is y. This is not equal to the derivative. What the heck is going on? This is y prime. Sorry. This is y rewritten. Y prime or dy dx is, what's the derivative of the outside? Cosine. With the inside the same. Times derivative of the inside. What's the derivative of the inside? 1/2 x to the negative 1/2. And then all the possible rewrites you should be aware of. That's the idea. All right. Lots to do today. We got 2 lessons to cover because I didn't teach on Friday, so we're busy. Here we go. The first one is the, I think I have the front sheet on it. It's, green. The implicit differentiation. Okay. This is an unfortunate day for 2 lessons because this one's a bit of a humdinger. All right, so first of all, it's just vocabulary, okay? An implicit equation is one where neither of the variables is alone on one side, or neither variable is explicitly found. Now, any equation could be written implicitly. For example, the explicit form y equals 2x plus 3. That's explicit because y is solved for. I could rewrite any explicit equation as an implicit equation like that, where y is not solved for. Okay, so just a little bit of vocabulary. Explicit means one of the variables is solved for. Implicit means the variables are all kind of mixed up in a jumble, not solved for. So is this implicit or explicit? It's implicit. Neither variable is solved for. The second one, implicit or explicit? Explicit is clearly solved for y. Y is explicitly or clearly stated. What about the third one, implicit or explicit? Implicit. A bit of a mixture, neither solved for. There's a bit of a mixture of y's everywhere. And the last one, implicit or explicit? Implicit, right? X's and y's mixed up. So we have done derivatives on explicit, when you have one variable solved for. Implicit is a little harder to take a derivative on, but you will, with the chain rule, be fine if you remember the chain rule, all right? Now, let's talk about how you might take the derivative on that y squared, right? Think of it, instead of y squared, what if I called it f of x? You know, y could be f of x. So what if I said take the derivative on f of x squared? Now, that right there is a function within a function, yeah? So the minute I have y mixed up and jumbled up, I'm going to have a chain rule issue. So what is the derivative on f of x quantity squared? 2 f of x to the 1 times f prime of x. All right, perfect. Now this is why you got to do your chain rule before you do implicit. You can't take the derivative on y squared unless you understand that chain rule idea. Now imagine, instead of it being written that way, we would write it as y squared. Now that's pretty common. Y and f of x, we're often using f of x instead of y, or y instead of f of x. So if there was a derivative of y squared, we would do pretty much the same thing. It would be 2 times y to the first, just like up above, we took 2 times f of x to to the first, we took the derivative of the outside. The derivative on the inside, that's kind of kooky, but when there's a y there, the derivative of the inside is dy dx. So when you have a y mixed up in the mix, you take the derivative on the outside, but then it's times the derivative of the inside, and the derivative of the inside is the derivative of y, and we write that as dy dx. Okay? So would you, is there something below that right there? Would you take the derivative of each of those? Change my notes a little bit. Would you take the derivative right below the box of those four terms? Let's take the derivative of the outside times the derivative of the inside, and the derivative of y is just dy dx. I need to paste this in. So I know it doesn't feel like, people feel like it doesn't feel like chain rule because it doesn't feel like a function within a function. But remember, y is a function of x, and so that's why it's a chain rule. Y usually depends on x, and so that's why when we see a y term, we also have to do this times the derivative of the inside side. So what'd you get for sine of y? Its derivative is cosine of y times the derivative of the inside, dy dx. The derivative times the derivative of the inside times dy dx. What about e to the y? Derivative of the outside, e to the y times the derivative of the inside, dy dx. 7y to the fourth, derivative of the outside, 28y to the third times the derivative of the inside, dy dx. The derivative of the inside is the derivative of y, derivative of y is just dy dx. And last but not least, cosine y. Negative sine y times the derivative of the inside, dy dx. Okay? Now, pause. It was my question when I was learning this. I said, how come that when I take the derivative of cosine, I don't do that stuff? I don't get it. So take the derivative of cosine. What's the derivative of cosine? Negative sine of x. Now, say I did do this chain rule. If I took the derivative of x with respect to x, what is derivative of x with respect to x? It's 1. And so it's kind of there. We just don't write it because it's, in this case, it's not a function within a function. It's just straight up an x. It's only when you have a y there that you would do this kind of idea. Are you with me? All righty then. I feel like this is out of order, so I have, where's that page? Oh, there it is. Darn it. No wonder. Okay. All right, so we did that. Now then, let's say we take, rather than the derivative of a term, of a whole equation. So if I took the derivative with respect to x of that whole equation, x squared plus y squared equals 9. Let's go term by term. When I take the derivative of x squared with respect to x, what is it? It's 2x. And if you were to do that chain rule thing, it would be dx dx. There wouldn't be anything there, right? When you take the derivative of y squared, that is a chain rule kind of thing. So the derivative of the outside is 2y times the derivative of the inside, dy dx equals, and what's the derivative of 9? 0. Okay? Now typically after doing this, then you have a little algebra to do. The question is usually, what's dy dx? Not just take the derivative and call it good, but find dy dx. So we usually then isolate the derivative term. So in isolating the derivative term, if we were to solve for this dy dx, then we could subtract the 2x over, then divide the 2y over to get dy dx, or the derivative by itself, negative 2x over 2y is negative x over y. Okay? Now we just talked about why we only use the chain rule on the y terms, not the x terms, because the dx is another issue. But let's shoot for the moon, and let's talk why this derivative rule, why that would give the correct slope looking at the graph. All right, so imagine the graph. What does the graph of x squared plus y squared equals 9 look like? Anybody? It's a circle centered at the origin with a radius of 3. Okay. Now this will make a whole lot of sense. Let's do a derivative rule check at this point here. At any point in this quadrant, won't the signs be positive x and positive y? Yes? In the first quadrant? How will the slopes come out sign-wise in that first quadrant? Well, according to the calculation, they'd be negative over positive over positive. All slopes are negative, and that makes sense for in quadrant 1. Don't you agree? What about looking at the picture? What would the derivatives or the tangent slopes be in quadrant 2? Looking at the picture. Positive. Looking at the equation, what will the slopes be in quadrant 2? Well, in that quadrant, x's are negative, and y's are positive. Won't that be then a negative, negative? And so, yeah, you're going to get a positive slope in that quadrant. That makes sense. Same is true for all quadrants. Let's look here. At this point right here, what's x? At the axis, x is 0, and the slope, therefore, would be 0. Likewise, down here, the slope is 0, and the equation or the derivative would be 0. Look at right here. That's vertical slope. Rise but no run. Well, wouldn't that slope be undefined at that point? And so that also makes sense because y is 0. We get undefined slope here. It's vertical. Because y is 0, here's 0 slope. Because x is 0. All right. All that makes sense. Last but not least, when I take the derivative on y equals x squared, what is the derivative? Talk to me. 2x, okay. Now, notice that the derivative on a function, is a function. In other words, if the original equation depended just on x, then the derivative just depends on x. If I wanted you to tell me the slope at any point on the curve, would you need to know an x and a y? Or if I just told you, tell me the slope at x equals 2, would that be enough? Just by knowing 2, wouldn't there be only one possibility, right? But on a circle, if I said here, tell me the slope at y x equals 2, could you do it? I don't know. At x equals 2, there are 2 possibilities. You would actually have to know both x and y to tell me the slope at any point, right? Now that is to say then that when you're dealing with a function like this, it makes sense that the derivative would have to depend on both x and y. I would need to know both x and y to tell the slope at any point. Just x or just y wouldn't be enough, right? So when you take the derivative on an implicit function, you'll often see both x and y in it, not just x like you did before, all right? We did that. What about the x and y axis? We talked about all those. In other words, the graph and the equation totally makes sense. That equation makes slopes like you would expect visually from the picture. All right? Let's go then to a full-blown example. So you got, find the derivative of x squared plus y squared, that big old conic section, which is actually a circle that's been shifted, but let's go with it. So when I take the derivative, I'm going to take the derivative of each term, or where one starts and stops with addition or subtraction. The derivative of any x term will be just like normal. So the derivative of x squared is 2x. The derivative of any y term, however, will have this chain rule part to it. So what's the derivative of y squared? 2y dy dx. Okay? What about the derivative of 2x? It's just a normal derivative. 2 plus the derivative of 3y. Now again, that's got a y in it, so chain rule. Derivative of 3y is 3 times derivative of the inside, so times dy dx. What's the derivative of negative 5? 0. And the derivative of 0 is 0. So, after differentiating or taking the derivative, you get a big mixture of x and y and dy dx terms. Now our goal is to find dy dx. So we want to now do algebra to isolate dy dx. How would you isolate or get dy dx by itself? Let's move all the non-dy dx terms over. I heard somebody say that's true. Dy dx and 2y dy dx and 3 dy dx can stay. I'm going to leave everything without a dy dx over, which would make them negative 2x minus 2 to the other side. Cool? Okay? Now then, how do we then separate or extract the dy dx's from that side? By design, every term over here has a dy dx, or a common factor of dy dx. So we can factor out the dy dx because they all now have that common factor and divide, and so dy dx then is negative 2x minus 2, that quantity over 2y plus 3. That's the idea on implicit differentiation. Take the derivative of each term, and anything with a y in it will yield a dy dx. Get all the dy dx's on one side, anything else on the other side, factor out, and divide over. Try those two on your own. First step there, check that you differentiated each term correctly. Check your answer to the first one. Did you get something like 2x over e to the y minus 1/2 y to the negative 1/2? Yes? No? Maybe? Okay. If not, call me over and we'll go over it. Otherwise, go over the next one if you were successful. By the way, depending on how you move terms, it's possible you could have an answer with exactly opposite signs on every single term, and that does happen, and that is okay. Ready? Let's go. Good? Lainey? Okay, so 2y, I did not take the derivative. So something like 2y's derivative is 2, but times the derivative of the inside, dy dx, plus, that's 3x to the half, so its derivative is 3 halves x to the negative 1 half. 1's derivative is 0. Sine of y is cosine y dy dx. How'd you do with your differentiating? Good, okay. How did you move stuff around? Did you move the 2 dy dx to this side, or what'd you do? That's only one move if you do it that way, I think. You could also, by the way, factor at the same time when you collect, and that's not terrible math. Okay, and then in the next step, show something like 3 halves x to the negative 1 half over cosine y. It's 2. Did you get 3 halves x to the negative 1 half over cosine y minus 2? Yes. Yay. Okay. When you get a product rule on these, mistakes happen. Mistakes are made. So be careful here. That's what I'd like to focus on now. When you get a product rule, you're going to have to go a little slower. So check this out. Together, let's look at this. When I differentiate with respect to x, I first have to find the derivative on xy. That's a product rule because it's x times y. So here we go. First stays the same. X times the derivative of the second. What's the derivative of the second? Dy dx. Perfect. Okay. Plus second stays the same. Y times the derivative of the first. What's the derivative of the first? That's the derivative of x, which is just 1, which I wrote 1. You could not write it at all. It's fine. Okay. Minus 2y. What's that derivative? Minus 2 dy dx. Perfect. Derivative of 6x. 6 and the derivative of 9. 0. Wonderful. All right. So let's keep the dy dx terms on that side and call it x minus 2 times dy dx if I also factor. What do I get on the other side then when I move non-dy dx's over? Negative 6 minus y. Therefore, dy dx is negative 6 minus y over x minus 2. Got it? Try the next one on your own, which has a product rule. Has kind of a weird back-end derivative as well. Check your product rule. Here's the product rule. X times 2y dy dx plus y squared. Also check your back-end derivative. It also is chain rule. 9 times the derivative of log y is 1 over y times derivative of the inside. All right, so this time I'm going to move that guy over because I have 2 terms over here. That'll be the least amount of moving, I think. 9 over y minus 2xy. I could write that a little cleaner as dy dx. So did you get something like dy dx is y squared plus 6 over 9 over y minus 2xy. Good. All right. Last but not least, and this is a huge source of error, just huge source of error, and that is, actually it's not last but not least, I have two more ideas. When you have a negative up front, people make mistakes on that negative term. I'm talking all the time, and because the multiple choices are chosen well, they will have that error in there as a distractor, and so you'll often lose this question because you deal with that negative badly. So let's go through this carefully. When I take the derivative on 7 cosine of x, what do I get? Negative 7 sine of x, and there's no chain rule component to that because it's an x, right? All right, now, it helps when you get to this to at least mentally think of that negative as being part of the first term. You'll make less mistakes if you do. So when I say first stays the same, it stays negative x cubed. And what's the derivative of the second? 2y dy dx. Okay. Now when I go to the second stays the same times the derivative of the first, and that second stays the same, so y squared. What's the derivative of the first? Considering that negative really is attached to that x cubed. Negative 3x squared. All right. In other words, both terms should have a negative because the you can think of it as distributing a negative to the product. Plus derivative of 3x. 3, the derivative of negative what? Negative 1 d y dx. Okay, cool. There are two terms with the dy dx. I feel like it'd be least moving if I move all the dy dx's to the right. If I do that, I'd have negative 1 plus, what's a cleaner way to write that dy dx term? It'd be positive when I add it over. Let's put the number first. So 2 x cubed what? You with me? Okay. And on the right-hand side, we have negative 7 sine of x. Let's go with minus 3x squared y squared plus 3. So at the end of the day, dy dx is 7 sine of x minus 3x squared y squared plus 3 over negative 1 plus 2x cubed y. All right. Last but not least, to prepare you for related rates. Sometimes, however, you don't take the derivative with respect to x, so you're not looking for dy dx. You're going to take the derivative with respect to some other variable that's not even in there, like time. That's pretty common in real-life motion-y problems. You want to know how does something change with time. So if, in this case, I'm given this equation, and I want to take the derivative with respect to time, x and y then are both functions of time. They're both going to be, both x and y terms are going to require chain rule because they're both functions within functions. So when I take the derivative of x squared with respect to time, it's the derivative of the outside, 2x, times the derivative of the inside. Now that's the derivative of x with respect to time. How is that written in calculus? dx dt, right? Plus, what's the derivative of y squared with respect to time? 2y dy dt. Plus derivative of 2x. 2 derivative of x with respect to times. Plus the derivative of 3y. 3 dy dt. Derivative of a constant is still 0. And so all good. Now, this one's going to look a little different. If I want dx dt, then I need to isolate dx dt. Let's say I keep these on the same side and factor out a dx dt. I'd have 2x minus 2 over there, right? Anything without a dx dt then needs to be moved over to the other side. So the dy dt terms are going to be over there. On that side then is 2y dy dt minus 3 dy dt. You could factor of dy dt out is fine, you don't have to. But your final answer then is dx dt is 2y dy dt minus 3 dy dt over 2x minus 2. Now, the idea of, what does that mean, dx dt, or change of x with respect to 2? What does that mean? Okay, we'll get there. And I understand it's frustrating to just be pushing symbols around without knowing what they, did I make a mistake? It should be, oh yeah, why is that negative? I don't know either. It should be positive, you're right. Yes, correct, thank you. The meaning will come. I promise you, but for now, I know, and it feels like a little symbol pushing. Once we get to the later rates, you can understand what to do. All right, you with me? The other lesson is far easier, and good thing, because we don't have that much time. So, all right, would you go to the other sheet, which is blue, I believe. This is set 35. That green one was actually the lesson for 34. 35 is really pretty straightforward. It's just 3 basic antiderivative rules. Right? Right. So, if I asked you to take the derivative of 3x with respect to x, what's the derivative? 3. If I asked you to take the derivative of 3t with respect to t, what's the derivative? 3. If I asked you to take the derivative of 3 theta with respect to theta, what's the derivative? 3. Okay, then. Here's the idea. All these derivatives were 3. And if I asked you to undo a derivative here, like, hey, what's the antiderivative to 3? Well, it could be 3x, because the derivative of 3x is 3. Could be 3t, because the derivative of 3t was 3. Could be 3 theta, because the derivative of theta, 3 theta was 3. And so that then has a bit of a problem in that it is not possible the way it's written. The only way we can know what the antiderivative was is if they include the differential to begin with. For example, it should always be written, any integral should always be written with the differential. The variable of integration was t, so that when you integrate, you know, oh, this must have been 3t plus a constant, and this must have been 3y plus a constant, and this must have been 3x with a constant. This is the differential. The differential tells the variable of integration. Or what the variable was taken with respect to when they took the derivative. I'm kind of crazy picky about that. In that I will count off on a test or a quiz if you don't have that differential there. It's crucial, all right? Now, second idea, know what to do with the coefficient integral. This is an easy idea. When you took the derivative of something with an integral, what did you do? A cosine of x. In other words, let's see, the coefficient just kind of comes along for the ride, right? Well, the same is true for integration. If I integrate 3 cosine of x, I could say, I'll just do that later, and right now I'm just going to integrate cosine and attach the 3 after. So what is the antiderivative of cosine? Sine or negative sine? Sine. 3 sine of x. When you integrate, you think, oh, there could have been a constant there. Don't forget the plus c every time, right? So the constant, or the coefficient rather, just comes along for the ride, just like in derivatives. Cool? Yes? Oh, I thought somebody said Mr. Yes?
The first one should be negative.
The derivative of sine is part of it, isn't it? The derivative of cosine is negative. Yeah. Sorry. Yeah. The integral of sine would be negative cosine. You're right. Okay. All right. Power rule. this also makes tons of sense here. When I take the derivative by power, what's the derivative of x to the fifth? 5x to the fourth, yeah? So in plain old English, if you were to explain this so even a 7-year-old could understand, actually you could teach a power rule for a 7-year-old, but in plain old English, when we take the derivative, we bring the x multiplied by the exponent by the old exponent and reduce the power by 1. Right? Isn't that the rule? Okay? So if the antiderivative is the opposite, what do you reckon we do? Instead of multiply, we divide. Instead of by the old exponent, we divide by the new exponent, and we, instead of reducing the power by 1, we increase the power by 1. We're undoing the derivative. So it's actually undoing every effect. Now then, if I were to say what's the derivative of x, antiderivative of x to the 9th, then it is x to the original power must, instead of been 9, must have been 10. And instead of multiplying by a power, we divide by a power and don't get constant integration. Now, we can always check. If I take the derivative on x to the 10th over 10, the 1/10 is just a coefficient, so I just leave it. What's the derivative on x to the 10th? 10x to the 9th. Isn't that exactly equal to x to the 9th? And so that seems like our integration worked. Remember, you can check an antiderivative with a derivative. All right, so when you integrate with a power, you raise it by 1, divide by the new power. All right? So try those on your own. You might consider doing a rewrite step, just like in derivatives, rewrite when necessary. Raise it by 1, divide by the new. Good? Okay, so the power here was 1. If I raise it by 1, divide by the new, it's x squared over 2 plus c, yeah? What about the antiderivative of x cubed? The fourth over 4 plus c. If the power here was x to the half, then when I raise it by 1, it's x to the 3 halves. Divide by the new, you could write it that way. You could also, I suppose, write it this way. Either one is fine with me. Do you agree?
Yes.
Okay. This, what is the power? Is it x to the 7th? It's x to the negative 7th. When you raise it by 1, does it become x to the negative 6 or negative 8? Negative 6. X to the negative 6 over negative 6 plus c. This is the great gotcha of calculus. Is that x to the 0? It is not. What's that antiderivative? Yeah, that's natural log. Now that's the only hole in the power rule. That one is the great gotcha. That one's not a power rule at all. It's natural log. Okay? Don't forget the absolute values. All right. Putting those rules together then, what's the antiderivative of 4x? Now, the 4 you could bring out front, and then power rule x dx. What's the antiderivative of x dx? Raise the power by 1, divide by the new. X x squared over 2 plus c, and so the final answer could be something like 2x squared plus c, right? 3 to the x. We could pull 3 out front, anti-differentiate. What's the antiderivative of e to the x? E to the x plus c. Negative sine of x over 4, I can pull negative 1/4 out front. What is the antiderivative of sine of x? Is it cosine or negative cosine? Negative cosine. So actually the cleanest form of this would actually be something like positive cosine of x over 4 plus c. What about 2? This is a mess. Let's rewrite it. 2 can be brought up front. What is that as a power? X to the 5 halves. Now let's power rule. 2 stays out front. What's the derivative of x to the 5 halves? If I raise it by 1, divide by the new. 7 halves over 7 halves. I guess you could also say this is 2 times 2 x to the 7 halves over 7 plus c. Or I suppose you could also see 4x to the 7 halves over 7. What's the antiderivative of 7 with respect to time? 7 t plus a constant, right? What about this? Rewrite step. 5/4. What is that as a power? U to the what? U to the what power? It's hard to use the power rule unless you know power. 1/3 positive or negative? Negative 1/3. You have 2 algebra skills you have to demonstrate there. You know the negative exponent is from a denominator, and the root is the same as a fractional exponent. So, what is the antiderivative of u to the negative 1/3? If you raise it by 1, it becomes u to the negative 1/3 plus 1 is 2/3 divided by 2/3 plus c, which you can also clean up. All right, that is that. Questions on your homework from Friday? 70, not 70, that's the other class. 34 questions. Shout them out. Yeah. Oh, the notes. My bad. Yeah, sorry. So what's the antiderivative of a constant with respect to x? It's the constant times x. Now remember, that could be k dt, k d theta, but that differential tells you that when you integrate what the variable is. You with me? When you have a constant out front or a coefficient, you can bring it out front and then integrate as normal. That is kind of hard to do anymore because you don't know what f of x is. And then the power rule. If you integrate something with a power, you raise it by 1, so x to the n plus 1, divide by the new, so also n plus 1. Okay? Sorry about that. Okay. Questions on 34? 6, 4, 24. Did I hear 9? Maybe I didn't. 6, 4, 24. 21. 22. Did I hear 21? Did I hear 22? 21 and 22. 20 what? 23. 1. Okay. Let's see. Easy to be. These replacements. Did I, oh man, did I put the key to this one? 6. All right. Six. What else do I need? Twenty. 21, 1, 2, 3. Okay. All right, there we go. Okay, so I think this is 4, yes? All right. So, not moving. Let's translate this into calculus. Not moving means slope or velocity is 0. Velocity, how does it relate to position? Velocity is the change in position with time, so that makes it the derivative of position. Velocity is the derivative of position. If you don't know that, write that on your paper. Velocity is the derivative of position because it's change in position with time. So I need S prime. S prime is the derivative of 2t squared, which is 2t. Beautiful. That.
Good morning, Devil Jaguar. Please rise for the Pledge of Allegiance.
Wonderful. Excellent. I pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all. So part of the solve is that take out a great stone factor.
All students, there are lots of sound items, including things left in lockers last semester in the lobby. Please come see if you have anything there. Everything will be donated to charity on Friday.
JV football players, go to the locker room after next hour. The bus leaves at 2 o'clock. If you have any questions, Coach Stern.
Students, remember all of you are excited and encouraged to attend college visits during 7th hour. Please use Nanios to sign up.
So cosine is 0 at, cosine is 1 at 0 and 2 pi and 4 pi and so on, right? Now that means t squared used to be that, so t is the square root of each of those. That's out because it's a mean. So your solutions are any even
Mark your planners. The Denver
multiple of
National
pi
College Fair is
square
coming up on
root.
Sunday, September 30th from 1 to 4 p.m. at the Denver Mart. Over 300 colleges and universities will be visiting with me. Must pre-register. See posters around school to stop by counseling.
Seventh grade student council elections resulted in the following people being elected. Cal Foster as president, Max Monroe as vice president and representative, Tony Adams, Mateus Bauer, Kira Nadler, Alexei Sanders, Vishnu Kutera, and Devin Stevenson. Congratulations to those elected, and thanks for having a very spirited campaign all around. Our first meeting is today in Mr. Bean's room during 7th hour. Sign up with your social studies teacher as they come on over.
If you are missing from the first girls' mentoring meeting, please come down to counseling today and get your get-to-know you form so that we can order t-shirts.
Okay,
You love Chick-fil-A? Have you
this
seen
one's a little rough.
signs around school? Come and support Spanish.
Factoring by grouping means greatest common factor here, which I'll call negative x squared. Greatest common factor here, which I'll call negative 1.
Seniors, don't forget to ask the teacher in person before requesting a letter of recommendation in Nanios.
Today is the optional college essay workshop for seniors in counseling. This is a great time to focus and hopefully finalize your essay.
Seniors, are you overwhelmed with the Common App or other college applications? Never fear, your counseling is easier. Come down to counseling today during 7th hour for our Common App workshop where we can answer all your questions, help get you started, and or anything else you may need to make the process less intimidating.
Junior high students, on Wednesday, September 24th, 7th graders will gladly engage in our cafeteria.
Definitely, Jack. Congratulations to the marching team for a fierce performance on Saturday at the Monarch Marching Competition. The band placed first in 3A competition.
Congrats to the boys and expecting to have 18 special group performers. Brandon Pennington and Phoenix Lethal got first place in 1 Kenneth Palmer and Colton Stiller got second at 3L. Carter Smith got third in 3C.
So as far as cases, it's this case here. It has one horizontal tangent, so it has one extra. branches of fossil area. So, dv equals d prime dr dr. So that's something like pi r squared r equals 4. All right, have a good day. Cool. Yeah, I'm gonna do a few where it's not public though. No, I will not be putting these online. Do your best if you have questions, come in, but I want to see what you're doing without my help. I'll get a little too much copying. Oops, that's not going to push. Okay.
This is somewhere.
Oh, I have a seating chart somewhere. Where did I put it?
There's a seating chart.
Yes.
Outside the chart. I want these.
Seating chart. Yeah, always forgetting that.
I know, it's really bad. It's only your class.
Why are the seats like this?
Why not? Variety is the spice of life.
I like variety.
Here, this is the seating chart. I will. Here's the board.
Want some gum?
I love a good paper. Okay, so if you look this way out there, it'll be clear. Third row. Thanks, Cal. Third row. Whatever seat. Shall you are. No, you're.
Wait, is this this guy?
No, new seat.
Oh, this
Do
is
we
a
sit
good seating
wherever?
chart. Hey, you're back. You're.
Dude, what's
Here's the
up?
seating chart right here. It's easiest if you look out this way. There's the board and
So I have all the Alright, so let me just look like this.
board doing that.
Wait, am I in the very Is there any seating for everybody?
Oops.
Are you sure this is how it's supposed to be?
Yeah. Are you?
It's easiest if you just keep it on the podium and